We use coordinate systems to be able to translate a physical event to a mathematical representation of that event by ascribing numerical values to specific points in space. So let's look at an event. This orange line here is the ground, and this blue, we'll say it's a small rock. I'm going to drop. I start about 50 feet in the air, and I have a stopwatch that I start right when I drop, and I see in about 1 second later it's fallen about 5 meters. And so this is a big picture. And 1 second later, after that, it's fallen about 20 meters from where I started. And another second later, it's fallen about 45 meters from where I started, about 5 meters above the ground. So this is an actual event. And of course, it doesn't change depending on how you represent it. It just always is. But I have choices about my coordinate system I'm going to use to describe this event. So let's choose a coordinate system. So I have a coordinate system, it has an origin, and it has a positive direction, and a variable associated with an arbitrary position. So I might decide that my 0 is here on the ground, and I might choose the positive direction to be up, and I might ascribe my variable to be x. And I said, well, it was right here was 5 meters above the ground. So here I added those distance I set at the beginning. It'll help me figure out what my coordinate system is saying. So this would be 30 from the ground, and this was 15 more, so this is 45 from the ground, and then this top was 50 meters above the ground. So this is my coordinate system, and these are the locations of the object relative to this coordinate system. And so now, if I wanted to create a tabular representation of this data, I could put time in seconds and position in meters. And I could say at 0 it was at 50 meters, and at 1 second it was 45, and 2 seconds it was 30, and 3 seconds it was at 5. Now I could graph this data. Here I've made a graph of x versus time, and at 0 it was at 50, and 1 it was at 45, so sort of halfway between there, and 2 was at 30, so that was here, and then 3 was 5, it was down here. And so I could sort of draw a curve through that data if I wanted, and it would look like this. This is the mathematical and graphical representation, or not math, the tabular and graphical representation of that data given this choice of coordinate system. But this wasn't the only choice of coordinate system I could have made. So here in green, I've created a new coordinate system where the 0 of my coordinate system, or the origin, is now where the ball started, the initial position of the ball. But I still have the positive direction going up, so positive up just like before. But since the ball is going down, that means 1 second later, where it's traveled 5 meters, on this coordinate system that would be a negative 5 meters, since it's going below 0 on my coordinate system. At 2 seconds, it had traveled 20 meters below the origin, so that's negative 20 meters. And at 3 seconds at negative 45, so it had gone 45 meters, so that would be negative 45 in this coordinate system. So for my tabular representation, at 0 it's 0, at 1 it's negative 5, 2 negative 20, 3 negative 45. And I can represent that on a graph. Here's 0, and at 1 at negative 5. These are in increments of 10. So there's negative 5. Here's negative 20 and negative 45. I get a curve. And so now you can see, while the physical system was the same, we chose a different coordinate system, which gave us a different tabular and different graphical representation. Now you might remember, even though the graph is different because we're going with negative values, the actual shape of the graph is the same. However, the shape of the graph can change as well. So I have the same physical system. I'm going to put the origin of my coordinate system at the position where the ball dropped, and then I'm going to create my positive direction to go down this time. And maybe I can give it the y variable. And so now that my positive is down, at 1 second, in this coordinate system, this location is identified with a positive 5 meters, and this location is identified with a positive 20 meters, and this location is a positive, associated with a positive 45 meters. For my tabular representation, which is time versus the y coordinate in meters, 0 is 0, 1 is 5, 2 is, now these are positive numbers, 20, and 3 is 45. Graph 0 is at 0 at 1 second, it's at a positive 5, 2 is at a positive 20, and 3 is at a positive 45. And so now my curve is curved, but it's curving up. The system is always the same, but you have choices about the coordinate system that you place on your system. Since it's imaginary, you have to choose where the origin is. You get to choose the direction of positive values, and you get to choose what the label is, the variable for that coordinate. And some choices will make the system easier to solve than others. So it's very important that you explicitly put a coordinate system on your schematic and make conscious choices about the origin and the positive direction.